Okay, welcome. My name's Maggie Johnson. I'm the Education Director here at Google, and it's my pleasure to introduce Team Antipodes, which are three high school seniors from Pacifica High School, or High School in Pacifica, Terra Nova, and two of which are here today to show you about all these wonderful gadgets and robots that you see in front of you. This is their third time here. They visited us in 2010 when they talked about their adventures in Istanbul, where they were competing in an international robotics competition. Since then, they've won numerous awards and competitions. Most recently, the Best Robot Design at the First World Championship this year in St. Louis, which is one of the most prestigious and prominent high school competitions in robotics. So they've really covered quite a lot of ground in the last 3 years. So they are here to talk about their design, their engineering process, and about how they're foregoing their last year of competition in order to mentor younger teams and sort of hopefully have them follow in their footsteps. So Team Antipodes.
All right. Thank you, Maggie. So I'm Kjersti.
I'm Violet.
And we are Team Antipodes. So we, like Maggie said, we just want to talk a little bit about our experiences, as well as what lots of other kids around the country experience through after-school robotics. And then we want to tell you about the design process that helped us win the Design Award at the World Competitions. And then we'll have a question and answer, and we'll drive around our robot and let you guys drive around our robot.
All right. So when people think about STEM education in schools, they think that each of the subjects are treated equally. However, from our experiences, science and math is covered a lot more than technology and engineering. In fact, you don't barely get any education about technology and engineering in schools. This is where robot design comes in. An organization which is trying to fill this gap is called FIRST. FIRST runs 4 different levels of student robotics competitions: Junior FLL for younger elementary school students, FIRST LEGO League for older elementary school students and middle schoolers, and FIRST Tech Challenge and FIRST Robotics Challenge for high schoolers. In our first year as a team, we competed in FIRST LEGO League, or FLL. This is our robot that we used, as you can see here. So in FLL, teams compete on a 4x8 obstacle course, which changes every year. They have 2 minutes and 30 seconds to complete as many tasks as possible to get a maximum number of points. Keep in mind that everything the robot is doing is autonomous, so everything it's doing is pre-programmed. Because of this, sensors are really vital to help navigate around the field. So every time you see the robot backing up against the wall, it's using a touch sensor to help it see where it is. FLL isn't completely about robots. Teams also have to complete a research project about an issue in their community. We completed a research project on maglevs, or magnetic levitating trains. We built a small working model, which you can come and check out after the presentation. We did so well that we were able to qualify to go to the Open European Championships in Istanbul. One of the most amazing things about going to this competition was finding how many similarities we had with kids from all around the world. We spent a lot of time from a team from Istanbul, and it seemed like they could have been from another high school in California. Our other teammate and I spent a few months in Tasmania, Australia with our sister team, where we competed in RoboCup Junior in the dance theater division. So we made a sort of autonomous robotic puppet show. While we were down there, we also competed in FLL again and became the Tasmania State Champions.
After a year of FLL, we spent 2 years in FTC. You can see the 2 robots that we made on our first year, our rookie year here, and our last year's robot right there in the front. Our FTC team has 3 to 10 high school kids, and in a match, 4 teams compete on a 12x12 field. 2 teams make up an alliance, and an alliance works together to score points. An interesting thing about the alliance system is that your partner changes with each round. So a team that you work with one match might be your opponent in the next. In FTC, we also use different materials, mainly metal, and with those, we're allowed to customize them with different power tools like what you can see there. The language that we use to program FTC robots is called Robot C, which is a variation of the C language, with some functions that are more specific to robotics, like programming your drive motors. The engineering notebook is another required part of FTC. The teams use it to record some of their design process, any notes or calculations that they make. And then computer-aided design is another asset that the teams have. Many teams use it to design some of the more complex parts of their robot, as well as just create models so people can see the robot. As you can see here, our robot is pretty dense, and so we created a buildup of all the different parts. So we start with the crate grabber, which we use to grab the crate that we lift up into the air using our forklift, controlled by a winch and its drive motors. We have to get balls into the crate before we lift it using the rollers shown there, which align the balls to be lifted up and then get sorted before they're dumped. You can also see here a lot of the different motors and servos and sensors that go into making the robot. Then we have our frame here with our drive motors and our vertical drive system. And then our arm that we use to control a bowling ball, which is another field element, and our plastic protective sides. At the beginning of the match, we have to fit into an 18-inch sizing cube. So you can see here, when we're fully extended, we don't quite fit in. But when we close ourselves up, we're nice and snug, and you can see our starting position. We were also able to create an animation using CAD so that we could show people just what all those different parts of our robot do. So here you can see when we pick up the crate and then lift it up a little bit, so we can drive over to the balls and then scoop them up, where they drop into the crate, and then after we lift it up, and then after that we lift it up. We get more points the higher we lift the crate into the air. Looks quite dramatic.
All right.
Now we want to show you some real matches. So the first 30 seconds of the match are autonomous, which is pre-programmed. So here you can see we're the robot on this ramp in the back. And so we're driving off and then going to turn and get the bowling ball. An interesting note is that we use quite a few sensors, just like in FLL. We use a gyroscope sensor to make accurate turns, and then an IR seeker, infrared seeker, to find the beacon that's in the corner, so we can score the bowling ball in the correct space. The next 2 minutes are teleop, or driver controlled, so the teams are allowed to pick up their controllers and drive around their robots manually. You can see sort of the chaos that exists on the field during teleop. So that's another reason that CAD animation is helpful, so people could see what's going on. It's also worthy to note all the different designs of robots that there are on the field. It's rare that there are two robots that look the same. So here we are at the front now, trying to drive up onto the ramp so that when we lift, we can get some extra points. During this particular match, we ran out of time, so we weren't able to lift all the way.
So in our first year of doing FTC, we were able, with this robot right here, we were able to make it to the World Championships in St. Louis. And then our second year with this robot in the front here, we were able to make it to the World Championships again and became the World Champions in Design. So in FIRST, teams are encouraged to reach out to their community. For example, we like talking to corporations and telling them about the importance of student robotics. We also enjoy letting kids drive around our robot. We find that often sparks an interest in technology. They're often also stunned that they actually can drive the robot, because so many times they aren't allowed to interact with expensive machinery. When our local libraries were having the whole community read a book about Mars exploration, we turned this robot on the table here into a Mars rover by attaching a wireless web camera to it. And other kids could drive the robot around from a control room where they couldn't actually see the robot. There's also a collaborative spirit within FIRST. For example, we mentor a younger all-girls FLL team. And teams are also encouraged to share the knowledge that they have gained with other teams. For example, when we got started out in FTC, we didn't know what tools we should buy. So we looked online, but there wasn't really any information about it. So we decided to make a presentation about it and along with specifics about tools that we found helpful, we also address safety hazards concerned with those tools. After winning the World Design Award in our junior year, we figured the most logical thing for us to do in our senior year is to actually establish robotics programs that would last beyond our graduation. So I established and coached a team at an FLL team at our old elementary school. And Kjersti here has established and coached 2 FTC teams at our current high school.
So another thing, after we won the design award at Worlds, we were approached pretty frequently about how we designed our robot. And as we described the process that we went through, we realized that that was sort of what was unique about it, that we had a process for designing it all. So we put together a presentation so people could see some of the steps that we went through. And since some of you might be engineers, we thought you guys might be interested to see what we did. So as you can see, there are a lot of different steps to our designing, the first of which have nothing to do with design. There's a couple prep steps that we want to go through, starting with building the field that you'll be competing on. So when we built the field, we were able to get a sense of how much room we'd be able to work with, as well as what kind of obstacles we'll have to maneuver around on the field.
After building the field, the next thing we wanted to do was understand the game. If we didn't understand the game rules correctly, we would end up building the wrong robot.
Understanding the allowed materials is also very important. We are allowed to use mainly parts from a kit called Tetrix, as well as some parts that you can buy outside, like plastics. But we also emphasize not letting ourselves be limited by the materials we're allowed to use. In the middle here, you can see a nylon sprocket, and on the sides is that same nylon sprocket with the sides shaved off. And then we eventually made that into an Archimedes screw.
The last step of the preparatory things that you want to do is to drive last year's robot on this year's field. Sometimes you can you'll learn very quickly about essential things about the game, and sometimes you'll find things that you can reuse. For example, on this robot over here, we had a sort of fork that we used to control a field element. And we realized it was really great for maneuvering the bowling ball. So just with the addition of a few extra pieces, we're able to have our bowling ball capture.
Now that you've got all those prep steps done, we could go into the real design process, which starts with strategizing. Before you start designing, you have to know what you want your robot to do. We found working on a whiteboard to be very valuable so that we can get all of our ideas out there and then use some pictures to express our ideas too, to make sure that everyone is on the same page.
After we figured out our basic strategy, it was time to research. So YouTube is a great place to look for past FTC and FRC challenges. By watching these videos, we could see very quickly strategies that have worked in the past and those that haven't. You also want to keep an eye out for devices that fit your strategy. For example, we knew we wanted to make a forklift using a cable and pulley system. So we found this forklift from the real world that did the same thing. And we used it as a reference as we went through our design process. Many of the things that you find in the real world will have manuals that show schematics and can give you a clue as to how you may want to design your robot.
After you've researched your ideas, it's time to identify what kind of subassemblies you're going to be building. So a subassembly is a group of parts that work together to accomplish a certain function. So here you can see a couple different ideas for different subassemblies that we've had, again using the whiteboard. And you've already seen this build up, but it also shows how all the different subassemblies that go into building a robot and how they all work together to make one cohesive robot.
Once we figured out what we want to put inside our robot, it was time to give them some space assignments. So space planning anticipates subassembly conflicts, allowing more complexity and better access. One mistake that's really easy to make is to just put subassembly on top of subassembly as you think of them. However, this is going to make any of these inner subassemblies completely inaccessible, and when one of them breaks, you're going to have to take apart half your robot to get to them. So what you want to do is plan ahead and make all your subassemblies accessible from some point, either from an exterior access or an interior access. So here's a space planning diagram that we had for this robot in the front here. And in this picture, you can see the different access points that we had. We had exterior access points from the sides and the top, and then interior access points from the back into the sort of cavern.
Now that you've got your space assignments, the order of integration sort of goes hand in hand with that. You have to decide what order you're going to install your subassemblies so that they don't conflict with each other. And it also creates a sort of build schedule for the team.
So now that we had the overall planning done, it was time to go dive into developing and building each one of the subassemblies. So the first step in this process was to list the requirements and the constraints for the subassembly.
After you know what you want your subassembly to do, it's time to brainstorm different designs that could accomplish that. So the way we like to do it was we would have an idea proposed, and then the whole team would kind of talk about it, critique it, maybe piggyback on it and improve the idea before it was approved. So again, we like to use whiteboards a lot to discuss this because there's some ideas that when you try to describe them in words, the message just doesn't get across. And drawing can be a much better method of communication.
After you brainstorm, sometimes you have an idea which you're not quite sure if it's going to work or not. So that's where you want to have a proof of concept. So this is an expedient mock-up to test a concept. For example, we didn't know if 2 chains could in fact lift a ball up in the air, so we threw together some sprockets, some chains, some motors, and tested it and found that they in fact do.
After you've got an idea that looks like it's going to work, it's time to identify how this subassembly might interact with other subassemblies that you have. So you can see here we have gears and a sprocket that are doing 2 completely different things but are in very close proximity to each other. So we mocked it up to make sure that they weren't going to conflict when they started working. Then this is an example of several subassemblies that work together to accomplish a task. So on the outsides here you can see 2 rollers that keep the balls aligned while these zip ties push them towards this chain at the end, which will lift them up to later get dumped into a crate.
Once you have identified the subassembly interactions, you want to mock up your idea. So mock-up is a crude physical arrangement of parts. Oftentimes screws don't even need to be involved. Here we just place some pieces on top of each other to see if they would fit within the space requirement. And here we only built half of the roller for testing.
And next that you have an idea that looks like it's going to work, you're going to need to test that idea out. So here you can see the half roller that Violet was talking about with added weights put on so that we could make sure that we're accounting for weight that will be later added on in extra parts. And here you can see we're testing if the zip tie is going to actually push the ball along as the robot is moving.
After testing, it's time to optimize your idea. So optimizations which are helpful in FTC is making something smaller, stronger, more reliable, redundant, more accessible, and sometimes faster. In CAD can be very helpful during this process. So in this picture, you can see sort of before and after of optimization. Over here, we have the more reliable version. And then we made our pulleys smaller. And this sort of S-cut we have in the channels here allowed the 2 channels to fit into a smaller space.
Now that you have an optimized idea, then you can start marking out and planning the kind of pieces that you're going to cut so that when you do cut them, they are accurate cuts and you don't have to redo anything.
So for the 5 steps that you see in the gray box, those are steps that is going to be really helpful to use CAD to help you through them.
So now that you have your pieces all marked up and ready to go, you can start to cut and machine them. This is a part of the process that's very helpful if you plan ahead, so that if you're making a lot of one piece, you can use mass machining techniques, and you won't waste any time doing the same thing over and over and over again.
So after you cut out all your pieces, you can assemble them. And so here we got into some more specifics that would be more helpful to FTC teams.
And the last thing you want to do once you've got a subassembly put together and you think it's ready to go, you need to test it out, hopefully with another robot. You can see this robot here, before it was complete, was a skeleton. And it just had a few subassemblies put on that we wanted to test out with another robot to see if they were actually going to work in a competition setting.
So a nice thing about this process is that you're testing intermittently. So it means that if something fails somewhere along the line, you don't have to go all the way back to the drawing board. You can just go back to the last time you know it was working. And a unique thing about our process, our design process, is the fact that we go through designing and developing and building each subassembly one at a time before moving on to the next one.
And also, as you're designing, something that's going to come into play eventually is your wire management. As you keep adding things on, eventually you're going to get a robot that looks like this, and it's very chaotic, and it's not going to run very smoothly. So with the addition of one simple piece, we used a wire channel. We were able to control all of these along one route and have a robot that was a lot more clean.
So as we back out here, you can again see the sort of layout that we have for our design process. And at the end of the presentation we gave, we had another version of the video that you saw earlier, except this time you can see the gears moving within our vertical drive system. All right, so if you would like to see this presentation again or look at some other stuff about our team, feel free to go to our website, www.theonerobot.com. Also there, we have some resources for FTC and FLL teams. And if you're all interested in getting involved in any of the 4 levels of FIRST, please contact us through our website, and hopefully we can put you in touch with someone in your area.
So now we're going to do some demos and let you guys drive around our robot. And if you have any questions, please feel free to come up and ask us. And if you want to take a closer look at the robots, please feel free to do so. Thank you.
Really quickly before we do that, just want to show you the one thing with this robot is the arm lifting up in the air, so you can actually see it in real life. All right. Yeah. All right. Sorry. All right. There we go. All right. There we go. All right. So there you go. It's all the way lifted up. So any questions?
How much time do you spend per year on these robots? And how many months, as well as how many hours per week?
The competition comes out in September, and for this robot, we worked on it until about January. And that's about maybe 2 to 3 days a week after school for 2 to 3 hours, and then 1 full weekend day at the beginning, and then towards the end it becomes pretty much every day after school for 2 to 3 hours, and then at least maybe like 10 hours, 12 hours on the weekend. So we haven't really added it all up. We get that question a lot, and we still haven't really figured it out.
So from the beginning of the project to the finished product, how many months? Not exact working hours.
It'll be about 5 to 6 months. Although competitions start in November, so teams can build their robot in like 2 months and then go to some preliminary qualifying rounds. But they continue from November until February. So you can go to up to 3 qualifying rounds to make it to the regional tournament.
And also between every competition, if you advance, you can modify your robot in between those 2 competitions. And yeah, so that allows you a lot of time. For example, with this one, we got it in early September, and the world competition was in late April. So we were working on the robot from early September to late April.
But this one is not your first robot, so when you start building this, you're already pretty experienced. So
yes, but the challenge does change every year, so we can't use the robot that we had last year to base our design off of it for most parts. We had the one bowling ball thing, but most of the time you have to start completely from scratch.
How do you allocate your time between the project and the robot design?
For FLL?
Is there no project in that?
No, there's no project in FTC. In FTC, it's just...
So I guess my question is FLL.
One thing is, like, I was the primary builder, so after I'm done building, then they start doing the programming. So while they're doing the programming, I started to work on the project. So that's how we allocated it.
Oh yeah, a lot of times it had to do with who had the robot. There was a lot of fighting about who could use the robot, the programmers or the builders. And so usually whoever wasn't using it could work on the project. And sometimes we did have days where we just said that we needed to work just on the project. Did you have a question?
Yeah. So when you build your concepts about different parts of the system, how many prototypes do you have to build and throw out because they don't work? Or do you usually build them, or you just like design them into the CAD system and simulate there?
The only one that we really designed fully in CAD was the forklift. In our first iteration, we had a 4-stage forklift, while this was a 6-stage. And when we wanted to make everything smaller so we could fit more stages in, we built that all in CAD so that we didn't accidentally machine 6 channels that weren't the right size or something like that. But for everything else, we generally do a couple iterations, but we don't build a robot and then take it apart and rebuild it. We make every little subassembly very independent of the other so that we don't have to rebuild the entire robot.
And you can figure out all the kind of power requirements as a battery, how much power you need just use the CAD system?
No, we don't use the power for CAD. We're only allowed to use one battery. There's one specific kind of battery that we're allowed to use, and we have to make sure that that will feed all of our power needs. So for this one, for example, we had to change the battery after almost every match because there are so many motors and it just sucked so much power out. Well, this one, it could last like maybe 2 or 3 competitions or tournaments before we had to change the battery again.
Yeah, but so how do you make sure that the peak power can output from the battery is enough for the
Well, unfortunately, we're not allowed to change how much power we're given. We have to use a certain battery. So we haven't really taken power into consideration when we build our robots. We just kind of build it to perform tasks, and if it has enough power, it has enough power.
Yeah. Yes?
So the robots that you show here, they're mostly for competitions, like you're given a task and you build a robot for your task.
Yes,
So
exactly.
I see that you're like super interested in robots. Like, what kind of robot would you want to build yourself? Like,
BattleBots.
I've always wanted to compete in BattleBots. Ever since our little year, I've been saying that we should make a flamethrowing one, but that has never happened. BattleBots.
So during the competition, is it allowed to you first push all the other robots out and you can one?
Well, they have a lot of penalties in this, so we're prohibited from being too violent.
So how do you get started? I mean, you started in the elementary school or in the high school?
We started in elementary school, but you can get started right in high school.
No, actually, we got started in high school.
We got started in high school, but we got started with FLL, which is a smaller league for younger kids.
Some people start when they're 9 years old and keep doing FLL until they advance on and end up doing robots for most of their school years.
But you can start your junior, senior year. We're mentoring this year, so there's a couple seniors on our team.
So you started doing this because you have such a strong interest in it, or because you happen to have a kind of school teacher who's good at this and
well, it was because our coach actually went to a sort of big seminar that had a robotics team there, and he got interested in. So he asked just a couple of us if we wanted to be on our robotics team. And we're like, sure. And Violet was really interested, and I just did it for kicks, and then it turned out to be really amazing, and continued with it.
Teacher at school?
No, he's just the parent of one of our friends. He's an architect. Yeah.
So if I could answer that too, I'm coach for my 2nd year here, and the answer is just do it, okay? I mean, I got 3 elementary school daughters, and we got them and a few other kids in their Girl Scout troop, and we just do Lego robotics, and the time commitment is really what you make of it. I mean, you guys have been totally awesome. Ours is we'll meet for 3 hours on a Saturday every week for, several months, and there's not the after school and all that kind of stuff. And again, it's what you make of it in terms of time commitment, but even that amount of time commitment is just amazing what the kids come up with. both in terms of the robots and also the projects. I'm sorry.
Yeah.
And it's just, my answer is just do it. I mean, if you work at Google, you're smart enough to do it. I guarantee you.
It also depends on the kind of kids. It was easy for us to meet after school because we all went to the same school. We'd all been friends for a long time. But if you're dealing with kids who live far apart or go to different schools or something, that can be another like scheduling thing that you'll have to take into consideration.
Online resource or community that is good to help young kids to start.
There's,
FLL.
yeah, there's tons of online stuff.
Okay.
I mean, they mentioned
There's
like the YouTube
lots
videos,
of
there's also
online
websites. FLL itself has all sorts of things and videos, and to be honest, you might feel intimidated by looking at this team. I do.
We're on the high end of. Our robots are kind of advanced and on the high end of it. There's a lot of teams that it's their first year and they're trying to figure out how to do it. And they have simple robots, but I mean, personally, from my experience, I was coaching a FLL team at my elementary school, and we just put in. I was really busy, so I didn't have that much time to put into the team, and so we met like once a week for a few hours, and we got a robot going. And even though they didn't do the best, the kids had the best time at the tournament. Like, they really loved it, and it really made them excited. Yeah?
It might help for you to describe the requirements of an FLL robot, because the kids there are not doing all that machinery and CAD stuff probably, and so that might seem for the people who are interested in coaching a FLL team, it might be a little more approachable.
Well, for an FLL team, I mean, you can see the robot we had over here. So no machines are involved. It's just Lego.
The programming language is different. You use NXTG instead of the robot C language that we showed you. And NXTG is just an icon-based programming with little blocks of different kinds of movement that you string together to make the robot move.
And kids pick up on it very quickly. Mm-hmm. It's really great for them for their first introduction to programming. So you just build it out of Lego. You can use any Lego pieces.
You order a kit, and it sends you the CPU, the processing unit right here, and it sends you motors that you can put together and other different helpful things. Sensors, we have sensors down here that you can use just to give you an idea. And there's also several different templates that it comes with just to get you used to working with Legos so that you can see how things fit together, just to give you ideas to bounce off of.
So there's sample robots where you just literally put this piece here, put this piece here, put this piece here,
Yeah.
and you've got the sample
So
robot.
Lego makes those CPUs as well?
Yeah.
Lego makes a kit.
Yeah, this is all Lego stuff.
We want to invite you to come try our robot setup. So does everyone want to try to drive it? Sure. All right. Yeah.